We are going to go to our last two presentations from Iowa State University. The first one would be Dr. Justin DAHLBERG. Is going to present on accelerated construction of pile foundations by means of elimination. Dr. DAHLBERG.
Great. Well, thanks for the opportunity to present this afternoon. My intention is to give just a real high-level overview of this project that will be kicking off this month. It is a project that's obviously both funded through the ABC UTC as well as our own DOT here in Iowa. As you mentioned, the title of this project is Accelerated Construction of Pile Foundations by Means of Elimination. In layman's terms, it means let's sharpen the pencil, let's create some efficiencies in our design and eliminate some of the unnecessary substructure that is currently being used on many of the bridges here in Iowa. Okay, so just as a brief introduction, through the efforts of this UTC as well as other organizations, accelerated bridge construction has largely been focused on superstructure and bridge decks. There's been a few projects that are concentrated solely on the substructure, so we feel there's an opportunity to potentially expedite construction of substructures and therefore expedite the overall project timeline. Here in Iowa, the bridge design manual obviously is largely based on AASHTO design guides, but what we've recognized in the standard designs that Iowa often implements is that there's a lot of conservatism in the foundation elements and requirements. That could be total number of piles, size of piles, or a combination thereof. So there's an opportunity here again to potentially reduce the substructure requirements and therefore expedite construction. Give you a little bit of a background on why we're doing this project. So we've recently completed another project for the Iowa DOT that was looking at the contributions of concrete encasement on their steel H piles. There is a standard design, which I will show you here in the coming slides, where steel H piling are driven into the ground and then encased either individually or as a group with concrete. That concrete is not considered in the design of the pile itself. So intuitively, we're missing out on some of the structural performance that exists when we include the concrete encasement. The initial goal of the previous project wasn't to determine the capacity for design purposes, but rather that for the assessment of existing pile bents when subjected to scour. The concrete encasement is only it's only encasing the part of the pile that is above the stream bed, so as to protect the piling from any debris or ice flows or other components or excuse me, other elements that may be flowing downstream. What we observed in our previous study, both in an analytical and laboratory portion, is that there's a fairly significant amount of capacity on their standard designs that they're not taking advantage of, especially in the case of fully encased pile bents. Here's just a brief shot of the standard. It's called the P10L standard pile design, which again is the concrete encased H piles. Certainly don't expect you to look over this detail sheet in any extensive way, but I do want to point out the bit of a blow up there on the side, on the right side, to give you a better depiction of what these standard pile designs are. So I believe you can see my cursor, but what I'm circling here, you can see the H pile driven down into the stream bed below, and then that portion above the stream bed and slightly below the stream bed is encased up to the pile cap. This is just a depiction of a singly encased pile, but the same standard is true of a fully encased pile vent, which I'll show you here on the next slide. So this is what it looks like post-construction. And you can see here on the right-hand side in these photographs, the singly encased H piles up there on the top, and then the full encased H pile vent on the bottom. Again, I'll just reiterate that historically, the concrete encasement portion of this construction is not considered in the design process. Give you some more background on our previous efforts. The first thing that we aimed to do for our DOT was to develop a pile capacity assessment tool. Again, I'll reiterate that initially what we were charged with was to assess existing pile vents that were subjected to scour. So below the concrete encasement, the steel pile is exposed, and depending upon how much of that pile is exposed, there were some concerns with the remaining capacity and what measures the DOT would have to take in order to either repair or provide additional capacity to that pile vent. Once that pile capacity tool was completed, we aimed to go forward with some laboratory tests as just a practice of validation. So just the photograph that you see there on the right, as well as the schematic you see there on the bottom, is just one example of some of the efforts we took to the lab. The piles themselves were tested in several configurations. What you're seeing is just one here where we encased a portion of the pile that was 20 feet long with 10 foot long being exposed, just steel only. Again, this is one of many configurations that we tested in the lab. Through this validation process, we found that the pile capacity tool was a good predictor of capacity, but in fact the results in the lab show that there is even additional capacity beyond that of our pile capacity tool. So going forward with this new phase, we are first going to take on, as is the case with many of our projects, a literature review, just to ensure that there's additional information we haven't already captured. If there is additional information we haven't already captured, we'll include that in our project. And then we'll first undergo an expansion of our pile capacity calculation tool. This was developed through a lot of finite element analysis, and the initial tool was limited to single piles and encasement of those single piles only, and primarily that of the standard designs that the DOT already uses. With the expansion, we aim to include pile groupings or fully encased pile groups, and include non-standard designs, so different cross-sectional dimensions of the encasement, different pile sizes that may not be already in the standard, and make this a fully comprehensive tool that is adaptable for not only design but also assessment of existing bridges. After we complete the expansion of that capacity tool, we'll be taking a lot of what we learned there and in the previous study into the lab and doing additional validation of different pile configurations and encasements, and primarily those that are fully encased or multiple piles grouped together. We intend to test those in a similar way to the previous efforts we undertook, so as to provide, again, validation of the calculation tool that we both created and will expand. And then finally, to wrap up the project, we'll complete just a final report to both produce and submit to ABC UTC, as well as our own DOT. I think I probably have hit on these couple points already, but let me just breeze through this slide. Again, with the expansion of our capacity tool, we want to include non-standard encasement sizes. We will be investigating inelastic buckling, and plastic yielding, as we did in our previous study. A lot of this is conducted through finite element model simulations. But then in the end, you know, it's great to have this tool, but if it's not easily used, it's really unfortunate and lost to the DOT users or end users. So we want to have an easy tool that they can put in their toolbox, that they can reference upon initial design, or in the case of a load rating engineer, one that they could reference upon situations where they're observing scour on some existing bridges. And then our task 3, our validation in the laboratory, is just a real quick snippet of some of the pile sizes, pile lengths, and encasement lengths that we intend to complete in the lab. Obviously, don't have a lot of time to go on to the full laboratory investigation here, but it gives you an idea of some of our intention. So anticipated results for the project, obviously, is the revision of the bridge design manual for the DOT, or if not an outright revision, just provide a tool that they can use in conjunction with their current methodologies. We would anticipate that the tool would indicate a reduction in total number of piles and or the pile size, where they can both realize cost savings in materials as well as time for construction of the substructure, and then finally the expanded pile capacity assessment tool that they'll have at their ready and use. So with that, I will wrap up. Be happy to entertain any questions. But again, just want to give you a highlight of this project. Again, we will be kicking this project off this month, so certainly more to come as we get underway. But again, thank you for the time that you allowed me to present this. Harmon, are there any questions that I can answer before we pass it off to our last presentation?
Yes, Justin, if you give me a little time, I think we have a few minutes. I have a couple of questions to ask, if you would. So you anticipate that because the whole idea is that we would save time and cost with using this tool. So I'm guessing you have that some confidence level based on your previous study, no? Is that true? You have some results there showing that the capacities that code gives is less than what you would calculate with this tool?
Yes, that's exactly true. So again, the initial project, you know, there's a considerable effort towards just numerical simulations, finite element modeling, and that indicated already a an increase in the capacity over what's currently found in the standard design. But we wanted to take a step further and make sure that that tool was validated, and thus the reason to bring it into the laboratory, where we were able to test a number of pile specimen sizes and encasement configurations. But really the DOT, their interest lies in there's efficiencies in cost and time by the full encasement of the pile grouping, and so they're leaning towards that as being their primary practice. But intuitively, both their engineering judgment and through our laboratory testing, they're saying, hey, you know, this pile encasement that we're not considering could really benefit our substructures by reduction of materials, you know, number of piles or size of piles, as well as you know, if they can lean into the full encasement, there's a great time savings in construction. So it's really, you know, they're excited to see what we find, but you know, they want to obviously lean into more than just their intuition. They want a tool that can be used to you know, just provide actual design capacities, a tool that's been validated on our end.
Yes, and that's nice. And the last question is that you showed one test from the previous project and a couple of pictures for the new one. So again, for myself, it's a question that the in-case part is clear. That is what will be done, and we know exactly what it is. But the bare steel piles, what would be the length of it? I mean, what is the point of so-called inflection point or fixity point?
Yep. So this slide here gives you an idea of so our full pile length, and then how much of that pile is encased. This is not the full and exhaustive laboratory intent here, but it certainly gives you an idea. So as an example, an HP 10x42, this top line with a pile length of 16, and we have no encasement length, just so we have a baseline set of data that we can assess, or we can compare to these others where we have you know, a bit or the same pile length with a 10-foot encasement, or a longer pile length with a even longer encasement. So you can see there's a number of different configurations, but to answer your question, you know, we're ranging anywhere from no encasement to 30 foot of encasement.
Okay, thank you very much, Dr. DAHLBERG.